Good morning. My name is Pete Burns, Technical Sales Representative working with the Energy Conservatory out of Minneapolis, Minnesota. Today's webinar will be on air leakage and duct tightness compliance testing for the 2009 and 2012 International Energy Conservation and International Residential Code. The agenda for this morning's webinar will be, I'll give an overview of the International Code status. I'll review the 2009-2012 code language as it pertains to envelope and duct tightness testing. And we'll look at how some states are dealing with some of these new code requirements. The 2009 IECC, International Energy Conservation Code, was a pretty big departure from some of the previous versions in the code. In one key aspect, it was really the first time in the I codes that we actually had we had a performance testing option in the air tightness requirements. That for the first time in the codes, you could choose to either do a visual inspection of the air leakage sites, or actually do a blower door test with a pass-fail metric attached to it. 7 air changes at 50. On the duct testing side of things, the duct testing requirements, first time that we had any kind of a requirement, and this one was specific to ducts that were located outside the condition envelope. But again, this was all a kind of a long time in coming, and for those long-time testers, a welcome change in in the code language. Bear in mind that states are free to adopt the I codes either in their entirety by reference, or they can do amendments and kind of pick and choose what sections or what language they want. So they can pick and choose, and they can modify with state-specific amendments. And some of these amendments have really helped in some states clarify some of the questions or issues that people have with the code as it's written. But always bear in mind that the I codes are always a work in progress. As we speak, there's revisions and changing occurring all the time. That if you're interested, you can certainly get involved with these code changes at your state level. A good example of some of these amendments are going to be what happened as the state of Georgia adopted the IECC, and I'll review those a little bit later on. Code status as of October 1st, 2012. We can see that on this map that for the most part, states have adopted the 2006 International Energy Conservation Code. Many states have moved up to the 2009, and a handful of states have either adopted, really one state of Maryland, up and running with 2012, with a handful of other states poised to adopt the 2012 provisions of the IECC. A good source of information about the codes would be the Building Code Assistance Project and the Ocean Energy Code website. These two websites are really the go-to sources of information for code activity. You'll find actual maps on both the commercial and residential side of things. You can you can click into your state, see what's going on in your state, and there's actually even contact information to talk with local code officials about some of these issues. So again, BCAP and the online Code Environment and Advocacy Network, or OCEAN websites, good source of information for code issues. The Energy Conservatory, obviously we're an equipment manufacturer, and we provide technical support to our customers day in, day out. We get calls from customers in states that have either adopted these new provisions or are poised to adopt these provisions. And what we tend to hear, we hear from the actual folks that are doing these tests with questions about test procedures, protocols, code requirements, and whatnot. And what we're finding, there's a couple of reoccurring issues that pop up, and just to highlight these before we get into the nuts and bolts, to keep these in mind as your state. Once you become familiar with either your state language or what your state is about to adopt, keep in mind some of these issues that we found. First and foremost is that the I codes, as they're written right now, either the 9 or the 12, are actually silent in terms of referencing any kind of a code of a test standard. An example of a test standard that is cited in the code on the commercial side of things is going to be the 2012 commercial provisions. Will cite ASTM 779, and that's an actual test standard. Another example of a test standard that folks that are familiar with our test equipment and our some of our software for years, people using automated software have tested to the Canadian General Standard Board test, another test standard that has very specific requirements. HERS readers are familiar with a test standard, the HERS or ResNet test standard, the new ResNet test standard, something to really keep your eye on. And if you're not testing to that standard, that's something that you might want to download and start taking a look at. That is a robust and repeatable test standard that I think really deserves a good close look, and get familiar with that one. One of the other issues that pops up is who gets to do the test? Does the code specify any type of credentialing or training requirements? And all we're going to find out of the codes is that there may be language in there that says, where required by the code official, testing may be conducted by an approved third party. So unless your state adopts specific language that addresses either of these two issues, it will get down to the local authority having jurisdiction. The local, either building official or code official, would be the person that you really may want to make contact with. If your state's already up and running, give these guys a call, get in contact with these local code officials, find out what, if any, requirements they have regarding whether or not they're going to require testing or whether they're going to require specific credentials. The final small point just has to deal with the fact that the code, if you're going to be doing an actual performance test on the air tightness requirement, the International Code uses air changes at 50 as the actual metric that's used to verify or assess compliance. ACH 50 is a volume-based metric, and as such, someone will have to calculate the building volume. And this may be something that, if you're looking at getting into this, you may want to address these issues in advance with either your builder or the code official. If we had to cite a standard on how to calculate building volume, back to the ResNet standard, ResNet cites an ANSI standard, Z765-1996, that actually is a measurement standard that uses exterior measurements. It's a small point, but it's a big deal that if we're not all on the same page as to how we're measuring building square footage and then building volume, that can really affect the actual numbers that we're generating. And this is really all as an aside. Historically, envelope testers, there's quite a history of having the metrics change on us. Old timers are quite familiar with just coming in and doing a single point testing for CFM at 50, and then having to interpret those results for homeowners. And the issue with that was that it's a very raw number. It's not normalized for either square footage of conditioned space, square foot of surface area of envelope, or a volume-based metric like air changes at 50. Code Council went with ACH 50 initially. Back to the 2012 IECC commercial provision. The commercial provision actually uses one of the newer metrics, which is CFM per square foot of surface area of envelope, and that's a metric that's really gaining traction. We see that again in the 2012 IECC commercial provisions. It's also the metric that gets cited by the Air Barrier Association of America and another test standard or protocol. The Army Corps of Engineers / Air Barrier Association of America test protocol also has the metric reported in CFM per square foot of surface area of envelope, and that surface area of envelope being defined as the six-sided box, the slab, the four walls, and whatever constitutes the lid or the ceiling of the building, whatever separates the building from the interior and the exterior. Okay, jumping into a little bit more about the codes, relationship between the IRC and the IECC. The IRC, International Residential Code, tends to address all topics related to residential construction, structural, plumbing, electrical, mechanical, and historically has had some energy provisions. But the idea was that it allows builder a one-stop shop in terms of a code book. Historically, its Chapter 11 has covered energy efficiency. On the other hand, the IECC, the International Energy Conservation Code, is an energy code with both residential and commercial provisions. I believe it's the 2009 version of the code, the IRC has fully incorporated the residential provisions of the IECC. So they are essentially interchangeable, and what you'll see in terms of the chapters and the sections of the code, a numbering system. The way that I tend to remember it is on the IECC side. I'll see, if I see an R, I know it's the IECC because the IECC has a specific residential section and a C for its commercial sections. So if you see a C or an R, you know you're in the IECC. And the IRC provisions have always been found in the chapter Chapter 11. So you'll see the 1102.4.1.2 for the testing provisions, and they'll also now in parentheses you'll see the IECC reference in case you only have one of those books. But for the purposes of this webinar, I'm going to stick to the IECC and cite the IECC provisions, but again, they are interchangeable. So let's jump in. Chapter 4 of the 2009 IECC, Residential Energy Efficiency, Section 401, General Provisions, 402.4, Air Leakage, 402.4.1, Building Thermal Envelope. Building thermal envelope shall be durably sealed to limit infiltration. The sealing methods between dissimilar materials shall allow for differential expansion and contraction. And the following shall be caulked, gasketed, weather stripped, or otherwise sealed with an air barrier material, suitable film or solid material. And that key word there, air barrier material, is near and dear to my heart because here in Minnesota we've been dealing with air barrier language in our codes since about 2000. And it really was a breakthrough for us and our builders. And after, residential construction in Minnesota built after 2000 with this really specific code language that said we had to have a sealed and continuous air barrier. In Minnesota, there was a little caveat that it was on the warm and winter side of the envelope. Really changed how builders were putting things together. And what we saw from that point forward was really tighter and tighter building envelopes, to the point these days where builders in Minnesota are hitting less than 3 air changes just by routine practice. But this language kind of coincides in terms of air barrier materials. People ask, what is an air barrier material? Well, by definition, we've got that these days, that if you turn to the Air Barrier Association of America, and we've got a flat-out definition of an air barrier material. Air barrier material is an air permeance metric when tested according to an ASTM test 2178. 2178 test for air barrier materials, if I come in at 0.02 liters per second per meter square at 75 pascals, that constitutes an air barrier material. It also just happens to be the air permeance of drywall, and it's used as a control material. If we move up from materials, we talk about air barrier assemblies. And air barrier assemblies are a collection of air barrier materials assembled together using air barrier components to provide a continuous plane of air tightness for that assembly. Maximum air leakage of an air barrier assembly should be 0.2 liters per second per meter squared at 75 pascals. And finally, we talk about air barrier systems, which is a collection of building assemblies brought together using air barrier components to provide a continuous plane of air tightness for whole building enclosure. The air barrier system determines the air leakage of the whole building. Maximum leakage of a whole building should be 2 liters per second per meter square at 75 pascals. Again, the reason I'm bringing this up is because this testing, when we're talking about performance testing building envelopes, it's all about air barriers. You are testing the integrity of the air barrier in the building. And from the get-go on building plans, builders these days have got to be able to draw a continuous line around the building envelope and say, this is the air barrier. We are testing the air leakage rate of the air barrier system. So on any print or in any, when we're into the specifications of materials, we got to find where the air stops in the building envelope. Because we're going to, under the 9, we've got some options, but under the 12, with a mandatory requirement for a blower door test, we're going to be testing these building, the integrity of these air barrier systems. Just as informational, the Air Barrier Association and the U.S. Army Corps of Engineers has a test protocol for testing. This is a commercial test, but just to keep this in mind, that the Army Corps standard has a leakage rate of 0.25 CFM per square foot of enclosure, or that's kind of an interchangeable term for envelope, at 75 pascals. That's tested both positive and negative, but that is the Army Corps. That's a commercial test standard. So back to the 2009 IECC, the building thermal envelope. Where are these materials? What or where are they in the building envelope? Well, it lays it all out. It talks about all joints, seams, and penetrations, windows, doors, and skylights, openings between windows and door assemblies and their jambs and framings, typical utility penetrations, drop ceilings, chases, plumbing walls, knee walls, walls and ceilings separating the garage from conditioned spaces, behind tubs, showers, common walls between dwelling units, attic access openings, rim joist junctions, and other sources of air infiltration. In section 402.4.2, air leakage and insulation, we get the language that says the building envelope air tightness and insulation installation shall be demonstrated to comply with one of the following options given by section 402.4.2.1 or 402.4.2.2. 402.4.2.1, the testing option. Language says that the building envelope tightness and insulation shall be considered acceptable when tested. Air leakage is less than 7 air changes when tested with a blower door at a pressure of 50 pascals. Testing shall occur after rough-in and after installation of penetrations in the building envelope, including penetrations for utilities, plumbing, electrical, ventilation, and combustion appliances. So again, first language gives us an option in the codes, 7 air changes at 50. Lays out somewhat of a protocol. It says during the test, exterior windows and doors, fireplace and stove doors shall be closed but not sealed. It says that dampers shall be closed but not sealed, including exhaust, intake, makeup air, backdraft, and flue dampers. It says that interior doors shall be open. Exterior openings for continuous ventilation systems and heat recovery ventilators shall be closed and sealed. It says that I just unplugged my phone. I apologize. I was getting a beeping phone, but back to it here. The exterior openings for continuous ventilation systems and heat recovery ventilators shall be closed and sealed. Heating and cooling systems shall be turned off. HVAC ducts shall not be sealed, and supply and return registers shall not be sealed. So your ductwork, the internal ductwork through the building is going to be is not sealed, and the supply and return register is not sealed. The 2009 option 2 is a visual inspection option. So in lieu of an actual performance test or blower door test, under the 2009, there is still an option to do a visual inspection. And we get the language that says, where required by the code official, an approved third party independent from the installer shall inspect the air barrier and the insulation. Key issue on really any of these two options is, when does this occur? At what point does this inspection occur? I mean, if somebody's going to come in and inspect the air barrier integrity and whether or not the bypasses have been sealed, how is that going to be done visually on an attic that has been insulated? So, this brings us back to some of these age-old questions of, who's responsible for air leaks in our building envelopes? Who's going to seal them, and when are we going to get somebody in to inspect them? Some state amendments that have been made to help clarify some of these two issues. State of Georgia did an excellent job with their amendments to the 2009 IECC. Folks in the state of Georgia worked with an organization called South Face Institute, and they developed, they got an amendment that had specific language that created a classification of someone that could be an approved third party. It's called DET, Duct and Envelope Tightness Verifier. Again, they work with the folks at the South Face. All of this information about DET and some of the Georgia amendments are available online at the South Face website. If your state is still in the adoption phase, or even if it's adopted, a lot of states will review their codes and have every couple of years they'll have a review of codes, and it's never too late to make code changes. And if your state is struggling with this language as to who should do the testing or what are the requirements, the training requirements, this might be the South Face website, and the folks at South Face might be a great resource in terms of getting that language into your state code. The Georgia amendment came up with this language. It said, certified duct and envelope tightness verifier. A certified DET verifier shall be a certified home energy HERS rater, or a certified home performance with Energy Star contractor, or a BPI analyst, or there's someone that has successfully completed a certified DET verifier course approved by the Department of Community Affairs. So this really, this was an amendment that was put together working hand in hand with the folks at the Department of Community Affairs in Georgia. So again, HERS raters, Energy Star contractors, BPI analysts, or the final option is to go through a 1 or a 2 day DET verifier course. Another route that was taken by the folks in the state of Illinois. Illinois pretty much adopted the IECC language as written. So it was essentially silent on the this whole DET or who gets to verify. Basically, you're left with folks in Illinois were left with language that said the local authority having jurisdiction may require an independent third party. So what they did is essentially an administrative clarification, if you will, that if you went to the Illinois Department of Commerce, you can find information that talks about this position, that talks about how they've adopted the 2012 code. They and the folks in Illinois took that code. They did tweak the performance testing requirement. The 2012 code has the requirement down to 3 air changes in the colder climate zones. And what Illinois did was they adopted, or they tweaked it and made it 5 air changes at 50 as kind of an initial step into the code. But they actually will recognize and have a list of people. They're maintaining a list of people that have gone through this training, and they have the language that says State of Illinois does not endorse individual building diagnostic testers. And it's just essentially maintaining a list of people that demonstrate they are able to comply with the 2012 Energy Conservation Code. So they're doing some training in the state of Illinois, and I believe they offer you can get the DET training in that state. Back to the actual inspection, the things that if you were not doing a performance test, if you're not doing a blower door test in terms of the building envelope, the things that someone doing a visual inspection, these are the building components that they would have to report on and verify that those are sealed. This is a table that's actually in the I code. Some states, as in Georgia, came up with a beautiful graphic that lays out for builders and people verifying these various infiltration points. And this is a great tool if you can get your state to adopt this type of a graphic. But it goes through the various kind of the likely suspects of infiltration points in the building envelope. Got some under-knee wall bypasses and knee walls. Some other statewide amendments. In Pennsylvania, they actually specified an ASHRAE performance test, ASHRAE test standard 119, air leakage performance for detached single-family residential buildings. So they went with 7 air changes at 50. But they specified a test standard that they wanted people to test to. So if you're testing buildings in Pennsylvania, you got to test to 119. You got to get a copy of ASHRAE 119, and that is the test standard that you have to test to. The 2012, I mentioned this earlier, but the 2012 amendments actually tightened the requirement. It was, again, viewed as a first step at 7 air changes, but under the 12, the visual inspection option was removed, and now the language says the unit shall be tested and verified having an air leakage rate not exceeding 5 air changes in Zone 1 and 2, the southernmost part of the states, and 3 air changes for the rest of the country, Zones 3 through 8. And this is the code map. Once again, 5 air changes in the pink and red, and 3 air changes for the rest of the country. So it is climate zone by state and county. So you might want to check that. So again, who inspects or tests? Where required by the code official and approved third party independent from the installer. The authority having or with jurisdiction decides. And again, key metric on this is going to be volume. And I started talking about this a little earlier, but coming up with that volume, if you folks are going to go out and do this kind of testing, you're going to want to check with your builder partners or whoever's bringing you into the project and say, hey, who's got the volume? Who's got the square footage? Who's got the floor height? Who's got the volume number? Is there an easier way, rather than me having to go out and measure the building or doing the measurement from prints? Does the designer or the architect, can you guys make a couple of quick phone calls and have these guys pull those numbers off of their CAD programs? Some of these new CAD programs are very sophisticated, and in some cases they can hit a few buttons and they can have these numbers for you real quick. Personally, I'd like to see that information provided to the testers, because the actual pass-fail is based on a precise measurement. That number, that building volume, right now, if we're sticking with air changes at 50, which we are, that number really should be submitted when the plans are submitted for review at the code office, wherever builders submit their plans. That number should be up front. Everybody should be in agreement on that number. There shouldn't be any playing around with that number, and testers shouldn't be the ones that have to come up with that number. In that vacuum, testers will be required to come up with that number, and you may want to be paid accordingly. That if you've got to spend an hour, 2 or more actually measuring the building on site or doing a takeoff, you may want to charge more. Maybe something you want to eat for now, but it could add considerable time. It's something you at least want to think about, or for your fee schedule. So according to the international code, you're going to do a blower door test. Tells you that you got what conditions the building has to be in. Doesn't talk about a baseline measurement at all. It doesn't talk about anything else. It just basically just says go out and have at it. So you're going to go out, you're going to fire up your blower door, and you're going to depressurize the building by minus 50. You're going to get your CFM 50. You're going to multiply it by 60. You're going to divide it by building volume, and you're going to have your ACH at 50. There may be better ways to proceed on this, and as states that haven't adopted or are adopting amendments as they move forward on this, we may start to see reference to some test standards. And kind of the test standards that a lot of people are familiar with: ASTM 779, 1827, ASHRAE 119, the Canadian General Standard Board 149.10. The folks that are doing passive house testing are familiar with a European test standard, EN 13829. And again, the one that I think people really need to keep their eye on, HERS raters should already be familiar with this test standard, but if you're not, get a copy of the ResNet standard, become familiar with one of their 3 testing options, either the ResNet single point test, the ResNet repeated single point test, or the ResNet multi-point test. All of these test standards are going to have you doing a procedure where you're going to measure the baseline pressure 5 times on a 5-second average. You're going to subtract the lowest from the highest and come up with a range. If the range of those baseline measurements is greater than 5 pascals, you'll be moving into a higher test standard. If you're initially trying to do a single point test, you would move into a repeated single point test or a multi-point test. Under ResNet protocol, if you didn't do that, you would be, and if that baseline range was greater than 5 pascals, you would be testing to a reduced test standard, which would hurt a HERS score. So again, get a copy of the ResNet test standards. Keep an eye on this. I think the ResNet standard, because it's a consensus standard, is a great document that's out there in the public domain, and we all should be looking at that and maybe adopting that as a potential new test standard for the international codes. Something to think about. So if your building passes the test, life is good, pack up, head home. If the building does not pass the test, you're at crossroads as to whether or not you're going to help your builder partner find the air leaks, or whether or not you're packing up and heading home anyway. But some of the tools, time-tested tools for finding air leaks in buildings, working with obviously blower doors with infrared scanners, blower doors with smoke pencils and theatrical foggers, a technique called pressure diagnostics, and visual inspections. Let's take each one. Blower door with infrared. You're going to find an air leakage path through an investigation. You're going to view the wall before the blower door is on, and then you would view the wall with the blower door running, and then you would do a visual inspection. Here's what they look like. Under the naked eye, we'd see this room. We can see we've got some features. Looks like an attic hatch or scuttle. Some kind of an unusual plumbing pipe going up through the ceiling. Once we turn the infrared on, we take another look at it, and we can see some temperature profiles of the building, highlighting the plumbing stack. We've got some issues with top plates and a temperature difference between the exterior walls and the ceiling. Once you turn the blower door on, the assemblies really come to life, and this is kind of a classic shot of the telltale signature of an air leak with kind of a brushing effect or tendrils or whatever you want to call it. But the air leaks come to life. That's the beauty of infrared with blower door. So at this point, you could snap a couple of infrared images for later use, send the house doctors up to seal the air leaks if they have access to it, and then retest again if this was the main issue with your failure. If you crawled up in the attic, took a look, this is what you'd see. You'd see a plumbing vent penetrating the ceiling up into a vented attic space. So this attic space is directly to the outside, not a stitch of insulation, and some top plates. You can see kind of maybe some leaks over by the top plates there. The other tools that you could use a smoke pencil, which smoke pencil or a smoke puffer is great for a small isolated area. You can use it with the building either pressurized or depressurized. If you're standing inside the building and you've got the building pressurized, the smoke will pass to the outside of the envelope. If the building is depressurized, the smoke is going to come back at you. You can also work with in a larger area with a theatrical fogger. And here's a shot of Terry Brennan, a building scientist working on a commercial building. He's got the building depressurized, and what Terry has done, Terry uses a vacuum cleaner extension pole, and he is fogging looks like the roof wall juncture of a building, and he's got the building depressurized, and if he sees air movement, he knows he's got an air leak. This is Terry's rig. He uses, again, it's a theatrical fogger with a booster fan on a vacuum cleaner hose and some controls that he's put together. Another technique is called zonal pressure diagnostics. ZPD has been around since the 90s. It's a way of measuring series leakage. Essentially, you depressurize the house to minus 50 pascals and you measure pressures in the zones. And you're looking for, the pressures are a ratio of the leakage areas. Zonal pressure diagnostics will help you determine where the pressure boundary is. And pressure boundary is an old term for the air barrier in the building. And hopefully the air barrier and the thermal boundary or insulation are aligned. This can help you work with both attics and crawl spaces or other little zones in a building, side attics, and really can be one more useful tool in your bag of tricks. Zonal readings, if I've got an attic zonal reading of 25 pascals, means that the hole between the attic and the house is the same size as the hole between the attic and the outside. An attic zonal reading of 48 pascals with the building depressurized to minus 50 means that the hole between the attic and house is 1/8 the size of the hole between the attic and the outside. Zonal diagnostics can be used. The other thing you can use, tried and true, visual inspection, near and dear to those of us that spent our formative years attic ratting around ratting around in attic spaces. The visual inspection with a digital camera really can be something that everybody's got to do at some point in their career. But classic shot up in an attic, see something suspicious kind of poking through the insulation layers, and if you dig out, you can find a nice little bypass or an air leak that essentially connects the living space to the unconditioned space or the vented attic. Another shot looking down into the into the crevasse of the bypass, and in the wintertime you can warm your hands on these things. But another one, real classic top plate air leak with an electrical penetration. As you move the insulation aside, you can see there's a pretty good size air leak. If this building was being depressurized, you could use your smoke puffer to puff down at it, and it would draw the smoke down into either the electrical penetration or at the sides of that top plate. The duct section of the 2009 IECC, section 403.2, ductwork, language says that that for insulation, supplied ducts in attics shall be insulated to a minimum of R8. All other ducts shall be insulated to a minimum of R6, and the exception would be ducts or portions thereof located completely inside the building thermal envelope. The sealing requirements, mandatory sealing requirements for ductwork: all ducts, air handlers, filter boxes, and building cavities used as ducts shall be sealed. Joints and seams shall comply with the IRC section M1601.4.1. Building framing cavities shall be not used as supply ducts. And here's just a shot of some insulated ductwork running through an attic assembly. Once again, let's clarify that those sections that you are allowed under the 2009. You can still use building cavities as ducts. You just can't use them as supply ducts. Under the 12, they really clean up the language, and they're basically saying ducts, air handlers, filter boxes shall be sealed. No mention of using building cavities as ducts, and it clarifies that building framing cavities shall not be used as ducts or plenums. Under the 2009 IEC section 403, the sealing requirements. What do you seal? Here's a great shot of a supply and return plenum, nicely sealed with looks like with a tape and a mastic. Here's somebody working on the connection between the supply plenum and the air handler cabinet, again with a tape and mastic, both working together. Here are some, looks like some supply runs off a trunk line branching off, where not just the trunk line itself, but the flex duct connection, the collar between the two, nicely sealed. And there's a boot and a supply duct, all buttoned up nice and tight, ready for a test. And this is a central return filter box, where you can see even the inside of the of that box is looks like it's got mastic and tape on it also. The duct tightness tests, under the 9, you've got a couple of methods and a couple of times that you can come into the building. If the duct tightness shall be verified at post-construction, you could use one of two methods. You could use leakage to the outdoors. You'd have an allowable leakage rate of 8 CFM per 100 square feet of conditioned floor area. If you were doing total leakage, you were allowed 12 CFM per 100 square feet of conditioned floor area at 25 pascals. Some states, again, have amended these requirements. The Pennsylvania amendments came in, and actually they went leakage to the outside, less than or equal to 8 CFM. Total leakage, 12 CFM, but they specified a test standard, ANSI ASHRAE 152-2004, method of test for determining the design and seasonal efficiency of residential thermal distribution systems. So again, Pennsylvania citing an actual test standard. Questions you're going to have to ask yourself out there when you're looking at both insulation or whether or not you're even testing. Is the ductwork inside the envelope, or is it outside the conditioned envelope? Here's a shot of a conditioned attic assembly and a duct run going through it. Again, the two types of duct leakage tests. You can do total duct leakage, and you can either pressurize or depressurize the ductwork, where the duct blaster is connected to a central return or an air handler, and you're going to measure the flow needed to pressurize the ducts to 25 pascals. This measures all of the duct leaks. It does not differentiate between leaks that occur within the condition envelope or leaks that occur outside the envelope. Duct leakage to the outside, again, you're either going to pressurize or depressurize the ductwork. Duct blaster, again, is connected to central return or an air handler, but then you're going to use a blower door. And with the blower door, you don't necessarily have to take a reading, a CFM, a flow reading with the blower door. You're just using the blower door as a diagnostic tool to either pressurize or depressurize the building envelope to 25 pascals. And then you're going to use the duct blaster fan to equalize the pressure between the duct system and the building. So you're going to use your duct blaster fan to get the duct pressure back to zero, and then you're going to have what the CFM that results that is the leakage to the outside. So you're measuring only the duct leaks to the outside of the building. These tests under the 9 can be done either at rough-in. If you're doing the rough-in test, again, total leakage less than 6 CFM per 100 square feet of conditioned floor area. If there's no air handler, it's going to drop down to 4 CFM. Under the 2009, again, the exception is that duct tightness test is not required if the air handler and all ducts are located within the conditioned space. And here's some shots of some likely suspects with duct leaks. The dovetails at the takeoffs, and there is a total disconnect of a duct run, and this can cause not just performance issues if it's going outside the building, but this is a classic slide of deterioration of the sheathing, where you had duct work running through the ceiling of the first floor that separated the first floor and the second floor, and you actually had either a disconnect or you were actually pressurizing the ceiling, and there was lack of an air barrier. So what was happening was that pressurized space was driving moisture-laden air to come in contact with the first condensing surface, which would have been the inside face of the exterior sheathing, and condensation occurred, and you got deterioration of the exterior sheathing. But that is an air. This is not an intrusion issue. This is actually a duct leakage performance problem in a building. This is a classic slide sent to us from the folks in Montana. Paul Cheetah shared this with us from the state of Montana. This is what happens when you have a full-blown disconnect of a supply run up in a vented attic, and this is up in a bitter cold climate. Tremendous condensation and frosting and ice. Any duct leakage that is outside of the envelope certainly creates an energy penalty, as well as an indoor air quality problem if you've got return leaks that are sucking air through loose fill fibrous insulation. Duct leakage to the inside of the building may not be considered an energy penalty, but it can certainly contribute to problems related to air delivery, comfort issues, and be aware that sealing ductwork can create other issues, that the system's approach demands that you look at all of the various interactions that may occur when you change something in a building envelope. That sealing ductwork can create problems, and you always want to do last person out always wants to do a safety check, or a worst case draft test, or a CAS test, combustion appliance zone safety test, on the building to make sure that you haven't either created a problem or exacerbated a pre-existing problem. Finding air leaks, again, same concept, that if you're working with your builder or HVAC installing contractor partners, you do a test. If they pass, life is good. If they don't pass the test, what are you going to do? Are you going to have the capacity or the skills to be able to find an air leak? Here's a shot of one of the best performance contractors in the country, Mike Uniac out of Arizona, pulling out a trusty theatrical fogger. Mike was a classic article where Mike was pressure testing installs on mechanical systems, again injecting theatrical smoke into the system, and you can see here's an install where the smoke is pouring out right at the air handler cabinet, or a connection between one of either the return or the supply plenum. You can also use pressure pans. That is a traditional diagnostic tool. It's not going to give you a direct measure of the duct leakage, but it can help you home in on the leaky duct run. You'll depressurize the building by -50, and you'll learn to interpret the pressure pan readings that you get to determine which run is leaking. You can also use an infrared scanner. Here's a shot of an infrared scan of an attic looking down. You can see that the scanner is picking up hot spots in the insulation, and if you stop and dig it out, you can find potential problems, disconnects or leaks. That's all I've got today. Thanks for your time and patience. These webinars are posted on the Energy Conservatory website. If you have any questions, concerns, or issues, give us a shout anytime. Thanks very much. Bye now.